tools and methods, and then more or less 1 hour on the evolution of asteroids and comets through the atmosphere. Well, this is, I tried to put together the space debris and the asteroids in the spirit of the Stardust project, but you will see that at the moment, the two, for space debris and asteroids, there are two different communities working, and there are totally different approaches to the actually to the evolution of these objects. Basically, space debris, as you will see, is tools and methods for space debris evolution are developed in the aerospace engineering area, while most of the methods and tools for asteroids evolution are developed in other areas, geology, earth science. So let's talk about the re-entry flow. All these objects. So everything that I will talk about regards the one of the last part of the life for these objects. So from the entry in the atmosphere to the impact to the ground or the destruction at some point during the trajectory. So what is important is, of course, and it is peculiar to this last part, is the interaction of the object with the air. And during the entry flows are characterized by two main things: very large, very high velocities, and different properties of the atmosphere through the trajectory. So different velocities, very high velocities means that, for example, we are talking of 7 kilometers per second, 7 or 8 kilometers per second for re-entry from Earth, but we could also, for asteroids and comets, we could arrive to 20 or up to 70 kilometers per second. And of course, from the higher part of the atmosphere to the ground, characteristics of the atmosphere like pressure and density change a lot. So, and what happens is that in terms of speed, these objects pass through different regimes, which are, well, they start from the hypersonic regime and then eventually pass to, possibly pass to supersonic and subsonic regime. I will talk about this later. In terms of differences of characteristics of the atmosphere, what we have is that we can consider 4 different regions. We have, we start from the free molecular zone, okay? Then we pass to the disturbed molecular flow, to the continuum, which is also called the transition regime, to the continuum flow with slip effects, and to the continuum flow. This is, these are regimes which are characterized by density, actually to characterize them, it is commonly used the Knudsen number, which is dimensional number, the ratio between the free molecular mean path and the characteristic length of the object. So very high values of the Knudsen number characterize the free molecular flow, and very low numbers, so below 1 to the minus 3, characterize the continuum flow. this is quite a, well, the recognition of these different regions is quite important in the sense that they have to be modeled in different ways. And for example, for the two continuum regimes, we can use the normal CFD tools, which solve the Navier-Stokes equations with integrated Navier-Stokes equations, taking into account chemical reactions. And actually, for the two molecular regimes, we have to use different approaches because the continuum approximation is no more valid. And so what we have to use are tools that solve the Boltzmann equations, considering the gas kinetic behavior of the flows. And these tools are, for example, the DSMC approaches, direct simulation Monte Carlo. Let's start to define what is the hypersonic flow at this point. So well, I don't know, but probably most of us know that the flow is set subsonic if the Mach number, which is the ratio between the speed to the sound of speed, is less than 1. If we have in supersonic flow, if the Mach number is greater than 1, there is also this transition regime, the transonic region, which is about more or less when the Mach number of the free stream Mach number is between 0.8 and 1.2, more or less. What is one of the main elements characterizing transonic flows, supersonic and hypersonic flows are the appearance of the shock waves. They appear when the Mach number, or the free stream Mach number, is more or less 0.8. And basically they are the regions of the flow, which are here, like this. Regions of the flow where the properties of the gas change a lot and rapidly. So actually what happens is that across the shock wave, static pressure and temperature and density, so they increase very fast. And this is just to give you an idea of what can happen or which are some of the relations that can be used. These are the equations for the normal shock waves, and they are derived by considering the conservation of mass, momentum, and energy. So these are equations which are valid when the specific ratio can be considered constant and equal to 1.4 for the air. While normally gamma is a function of temperature principally and also pressure. So if you consider this, if you consider these expressions, you can see that if 0 is the characteristic, is the value before the shock wave, and 1 regards the characteristic after the shock wave, so you can actually see that pressure P1 is always greater than P0, T1 greater than T0, and ρ1 greater than ρ0. So since there is no work at all, there is no heat addition, there is no source of heat, the total enthalpy and the total temperature do not change. But what happens is that the total pressure downstream is always smaller than the total pressure upstream. And these are again with the same approach, the equations that describe the change in total pressure and total temperature. What happens to the Mach number? Passing through the shock wave, the Mach number and the speed of the flow decrease a lot. And using again the same approach, this is the relation that gives the Mach number after the shock wave. What is one of the main things that should be considered is the rapid increase of temperature after the shock wave. And we will see why this is very important. So, shock wave, we said, are a principal element of all the supersonic flows. So supersonic flow, when the flow is supersonic, we have a shock wave. These supersonic regimes is sharply defined, and it is starting when Mach number of the free stream Mach number is greater than 1. The chain, what happens is also that aerodynamic characteristics of the elements flying at or invested by the flow change a lot. For example, this is what happens to the drag coefficient. So what we have is a rapid increase of its value through the transonic region, and then a decrease of it. The same thing cannot be said for the hypersonic flow. There is actually no rule to say that a flow is hypersonic, not linked to the Mach number. A rule of thumb is that we can say that the flow is hypersonic if the Mach number is greater than 5. But actually what happens is that to say that the flow is hypersonic, we need to actually analyze the flow and see if particular phenomena appear. Particular phenomena which are actually linked, mostly linked to the increase of temperature. And we will see now a few of them. Okay. So, for example, if we have a very sharp element invested by a hypersonic flow, what happens is that the shock wave, which is this line here, is very close to the surface. So the shock layer, which is the region between the shock wave and the body, is very thin, and actually can easily, well, not can, interacts with the boundary layer. And so we have strong interaction, strong boundary layer shock wave interaction. Viscous interaction. Another thing that happens for hypersonic flows is the fact that the kinetic energy of the flow is partially transformed into energy and into increase of temperature. There are two phenomena. There is the fact that, for example, the viscosity increases with temperature, and that means that the viscosity, if the viscosity increases with temperature, the boundary layer becomes thicker. And another thing is linked to the fact that it is known that through the boundary layer, the pressure normal to the boundary layer, the pressure is constant. So if the temperature increases in the boundary layer, the density decreases. So what happens is that this brings to the fact that in order to have the same mass flow passing, the boundary layer should be thicker. So these two phenomena make a very thick boundary layer. That means that what is seen by the flow is actually some sort of different shape. The shape of the object invested by the flow is modified because the flow sees a different, very thick boundary layer. One thing, as I mentioned before, one thing that is that happens is that the specific heats, Cp and Cv, become function of temperature. So also the ratio, the specific heat ratio becomes a function of the temperature. And that means that we cannot consider anymore the ratio constant, and those formula that we used before are no more valid. What happens is also that we have, well, this is linked to the fact that we have chemical reactions. We have, for example, dissociation of some of the molecula. We have oxygen dissociation that starts, for example, at 2000 kelvins. And we have nitrogen dissociation that starts at 400 Kelvin. So we have this chemical reaction. We have dissociation and reassociations. Chemical reactions, and what happens also is that if we increase the temperature, because the temperature can easily increase with the Mach number, what happens is that if we are in regions just immediately after the shock wave, so between the shock wave and the body, we can have temperatures very high, temperatures behind 9,000 kelvins, and at that point what we start to have are ions, so ionization of the air. This is an example. This is just if we use the equations that we used before to predict the temperature just behind the shock wave, what we have is this curve here. So a rapid increase of the temperature with the speed. But if we consider chemical reactions, what happens is that considering chemical reactions means also that considering the fact that the specific heat ratio is no more constant, actually it is smaller than 1.4 for air. That means that the temperature is not actually increasing as rapidly as we thought. For example, why this is very important is the fact that considering or not chemical reactions can have a strong influence on what are the aerodynamic characteristics predicted by our simulations, our tools. And another thing which is very important and we have to consider is the fact that due to the very high temperatures, there is a transfer of heat from the flow to the body. And this is one of the main things that should be considered to analyze and simulate the evolution of objects through the atmosphere at hypersonic flow. So we can distinguish two main different contributions. So if the heat is transferred by the boundary layer attached to the body, that is the heat, the convective heat. But what happens is also that if the Mach number is sufficiently high, immediately after the shock wave we have very high gases at very high temperatures, and those gases irradiate. So we also have radiation heat transfer, so radiative heating. As I said, the contribution of the two different heatings depend on the temperatures, and so depend on the Mach number. So what we have is, for example, that for a polar entry, what we have is that the radiative heating was 30% of the total, while for much higher Mach numbers, so probes entering the Jupiter atmosphere at 60 or more Mach number, the radiative heating could be as high as 95%. So this could be, this is one of the differences if we talk about space debris and asteroids. Since the asteroids are coming at much higher velocity, much higher Mach number, what they experience is mostly radiative heating instead of convective heating. So this is what happens. This is a general scheme representation for a blank body, something entering at Mach 36. If we consider the external free stream temperature equal to 258 degrees, we have 11,000 Kelvin after the shock wave. This is measured. So this is the real number, more or less. If we use those equations that we've seen before, and you put the same number, so Mach 36 and T0, 258 degrees, what is the result is something like 160,000 kelvins. Okay, this is because those equations are no more valid, are not valid because we are using, especially we are considering only the same, only constant specific heat ratios. So this is the general scheme. We can see that there is radiation here, so gases immediately after the shock wave emit radiations. There is convective heat exchange from the boundary layer. But what happens is also, in order to properly compute the heating, the amount of heating that enters, what we have to consider is also that usually, especially for metallic or for some of the materials, these elements re-emit the heating. Okay, because of course, due to the fact that they are receiving heat, they are increasing temperature, and with the increase of temperature, they start irradiating. Okay, so in order to properly compute the wall temperature, for example, and heating, what we have to consider is a balance between those three elements. Actually, what should be considered too is not only the balance of these three, but also the fact that for metallic materials or also new versions of thermal protection systems for space vehicles, there could be very high conductivity. So what we have is that we need to take into account what happens, the mechanism that moves the heat from for example, from the stagnation point to other parts of the the vehicle. And only this way we can have a current balance, a current approach to compute, for example, the temperature, the world temperature. As it happens quite often, if you do not consider the full equilibrium, so the conduction and the radiation and everything, what you have is a conservative value of the heating that is entering and a much higher temperature. So it is a conservative approach if you do not consider all the elements, all the balance. So, as I said, in order to have the aerothermodynamic characteristics of our object, could be space debris, could be a space vehicle, could be the asteroid, if we want, we could use high fidelity models, so general models, which are could be very expensive. And they cannot be used basically for the entire trajectory, for each point of the trajectory, because at the moment that could be impossible.
What do the acronyms stand for?
Sorry?
What is CFD? And
computational fluid dynamics.
Okay.
So computational fluid dynamics, up to a few years ago, I always considered computational fluid dynamics as a general umbrella to call all the numerical approaches for fluids. Then, for fluid dynamics, actually CFD is only for continuum and only to solve Navier-Stokes equations. All the other methods takes different names. So people distinguish between CFD for continuum and, for example, molecular tools, which is, for example, the direct simulation Monte Carlo approach for molecular regimes. So when the continuum assumption is no more valid. Well, but what happens is that we are lucky enough that there are lower fidelity approach. So the difference between high fidelity and low fidelity is basically that high fidelity approach compute, take into account all the non-physics, and so they are very general. And usually, if they are properly implemented, they give a result which can be trusted and should have a less error margin. Low fidelity approaches are approaches which do not take into account all the physics, take into account simplifications. Could be, for example, semi-empirical models. Could be using asymptotical behavior of the flow. And but the fact is that usually simplified approaches are very, very fast compared to the high fidelity ones. So what I'm presenting here, for example, is a comparison in terms of pressure distribution and local heat flux between a code which implements the SMC and iFlow, which is a code developed by our center which implements simplified approaches. And as you can see, more or less, this is one of the first version of the code. More or less, the colors and so the values are similar, with a fraction of the computation. So the iFlow can take a few seconds, while the DSMC form can take on parallel machines a few days. This is the main difference. So codes like iFlow can be used to simulate directly all the characteristics of the vehicle during the trajectory, while DSMC form can only be used to simulate few points during the trajectory. And just to check that things are correctly done. Now, as you can see here, there are simplified approach to have the pressure distribution and to have the heat flux approximation, local heat flux approximation. I will talk about local heat flux later on. Just a few words, I spend now just a few words to describe what are basically what is the basic approach to have the pressure distribution in a simplified manner. This is done through what is called the Newtonian theory for pressure distribution. Okay, what is actually exploited here is the fact that is the old idea of Newton that cannot work for subsonic regimes or for supersonic regime, but it works quite well for hypersonic regime. So basically, many centuries ago, Newton said, well, actually conjured, that what can, well, to predict the pressure on a body, what could be done was just to consider the change of the momentum of the flow. That doesn't work. That didn't work, actually. It doesn't work for normal application because in this Newton could not consider or didn't know about the fact that in subsonic regime the perturbations travel upstream. And another thing that he didn't consider is that the viscous forces, so shear stresses. These things actually, if you consider the behavior of the particles of the fluid for hypersonic regime, what happens is that basically we have the behavior assumed by Newton. So what we have is that when the particles arrive on the surface, they basically change the velocity, and the component of the velocity normal to the wall totally disappears, and so we have an ordered stream of particles traveling parallel to this. So what we can do is to use this and to say and to compute the force on the surface as a time change rate of change of the normal component of the momentum. So if we consider this term as the mass flow impacting on this area, and this is the velocity normal to this area, this gives us the product, this gives us the time rate of change of the momentum, which is actually the normal force. From the normal force we can obtain the force per unit area, and then from this we can say that the force from the unit area is actually the difference between the pressure upstream and the pressure on the body, on the plate in this case. So what we have is that if we want to have the pressure coefficient on the body, which is basically the difference of pressure divided by the dynamic pressure of the free stream, we have this easy relation. So the Cp is basically a function of the inclination here, the angle between the flat plate and the velocity. This can be, so what basically people do is to locally linearize any body in 3 dimensions, and for each panel apply this. But basically they do not apply what we considered. They use all the tools, use different modified Newtonian theory. The easiest simplifications to have, easiest change to have realistic values is considering that Cp is a function of the maximum Cp here, which is the stagnation point pressure coefficient. And all the CPs then are a function of this max value and the angle between the local inclination and the velocity. So all the tools, all the simplified tools that we will review shortly, basically use this approach or modified, more improved approaches, but to give the pressure coefficient, for example. And the problem of this, there are few things that should be taken into account. Is the fact that this, for example, elements which are shadowed by others should not be taken into account because they are not directly invested by the flow. There are other considerations, there are interactions, so tools implement this, and then each one of them has a different implementation. And instead of having this simple relation, for example, they have coefficients which are a function or empirical functions of the Mach number or empirical function of the other properties of the flow. Yeah, Christoph? Now I will actually start the review of the tools and approaches used for the space debris for the space debris re-entry simulation. Okay, so we all know basically that there is the space debris, especially in the space debris in low Earth orbits, has a limited time and at certain point enter the atmosphere. So it is a problem in itself to determine when it enters the atmosphere, and it is not something that I'm going to do now. Is not something that I will talk about now. What I will talk about are approaches to see if the element, the object, will survive the entry, so if will impact, and actually if any part of it will survive. Well, I'll not spend time on re-entry statistics. We know that there is the problem, and many orbiting objects have already re-entered the Earth with only one claimed injury, minor injury, as we've seen yesterday. Claimed. I do not know if it is actually. So. What we know, well, statistics give us an idea of what is the percentage of a satellite's mass which will survive. Could be 10%, could be 40%. Actually, the actual percentage depends on many things. Depends on the materials, depends on the shape, depends on the and also on the weight of the re-entry object. Just some energetic considerations. So if you consider a low Earth orbit, so let's say 100 kilometers, the total, the specific mechanic energy for these objects is something around 3 billion joules per kilogram. So if you take into account this, and you think that this entire energy can be converted into heat, basically that will give you the idea that all the objects will not enter the Earth because they would totally evaporate. These are, for example, some values of heat or enthalpy of vaporization for some materials. And you will see that those heat of evaporations are all smaller than the specific mechanical energy. Okay. So, as far as I know, that was one of the first approaches to talk about risks for space debris. And many people, many years ago, thought that there was no risk because all the objects would totally evaporate or would be totally destroyed. But this is not actually the case, because not only a very small fraction of that energy is converted into heat. Generally, 1% of that is converted to heat, and that actually it depends on the shape, the re-entry conditions. So the fact that as we have as experimental data, as realistic data, the fact that pieces or entire object arrive on the Earth is the chance is much higher than what was initially thought. Okay, so what happens is generally speaking is that some of the components are immediately lost at an altitude which is at the very high boundary of the atmosphere, and then most of the elements, most of objects could actually separate or destroy at an altitude which is around 75, 80 kilometers plus or minus 10. And again, all the chances to survive depend on the structure, the shielding, the shadowing, for example. If some parts during the descent are shadowed by other objects, then they do not actually experience the strong heating, for example, and they can survive during the critical phases of the maximum heating. So what it is done, as was basically said in a previous lecture, is that at the moment there are some mitigation some standards that specify the upper limits for the risk, and there are tools that are used to see if the risks are higher or lower for the objects that are put in orbit. For example, one of the standards is the NASA and NASA standard. So basically, this NASA standard says puts down the principles that should be taken into account, should be considered to evaluate the casualty risks for people on Earth being hurt by space debris, entire objects or part of it, which arrive on the Earth. One of the things that was considered to develop the standard is that for human casualty, or to be considered dangerous or hazardous, an object should have an energy, a kinetic energy higher than 15 joules. So, and that gives basically a limit on the mass and on the speed of the object. What is said is that for uncontrolled re-entry, the acceptable risk for human casualty should not exceed 1 to the 10 to the 4, 10 to the minus 4, basically. And in somewhere also in the standard, in the document that I've read, which was dated 2012, they also say that ESA was going to propose something similar, but at the moment I do not know if that is the case.
Indeed.
It did, okay. So this is the thing. Okay. So in order to evaluate the hazard on ground risk, so the standard talks about an equivalent casualty area of the single debris, which is a combination of human risk cross-section area, which is a standard area for vertical projection of each person, which is 0.36 square meters. And then the equivalent casualty area is given by the relation there. So the total casualty area over re-entry events is basically this, given by this, which is the sum of all casualty areas, equivalent to casualty areas for all the elements that are surviving, when n are the number of elements surviving. And then this area is used to compute the casualty expectation, the human casualty expectation, given by the product between the casualty area, the total casualty area, and the average population density for the particular orbit inclination and year of re-entry. So it is computed, should be updated every year. And this is what is used to see to evaluate the risks, the human risk. Then on the standard, on the NASA standard document, it is specifically said that in order to evaluate the risk, people should use their tools, which are tools that we will see later, which are these: the DAS, the Debris Assessment Software, and the ORSAT, Object Reentry Survival Analysis Tool. So these tools, within these tools, there are also modules that compute the risk analysis and gives an idea of the level of risk of the objects and part of the objects through a simplified simulation of their evolution through the atmosphere. So in ESA environment there are similar tools, and especially the Scarab one, which is at the moment, as far as I know, the most sophisticated tool. Why Scarab is the most sophisticated tool, we will see later. But basically, all these tools do have more or less the same characteristics, more or less the same elements, and more or less the same multidisciplinary approach to the problem. What change a lot are the models which are implemented inside and the insertion of some assumptions. For example, DAS is the most simplified approach, while the Scarab is the most sophisticated one. And there is a reason why DAS actually is simplified. There is a specific reason, and we will see later why this happens. So all the what all the tools do is to integrate the equation of motions. Could be, depending on the tool, we can have a 3 degree of freedom approach. So there is no attitude simulation. It is a point mass approach. we could, and of course, the integration of the trajectory requires the aerodynamic and aerothermodynamic characteristics of the module, and a model of the atmosphere. Then there are modules that have to compute the effect of the loads on the structure, and actually see if the object or part of the object are deformed, destroyed, ablated. This is basically a list of all the parts. So what we have is a flight dynamic model of the object. That means equation of motion. Could be, as I said, 3 or 6 degree equation of motion, which describe the change of momentum and angular momentum of the spacecraft. What is important is each tool should have data on the mass, the moment of inertia, and models to compute the forces and moments on the object. Main forces acting on the object through the atmosphere flight are the aerodynamic forces, which basically are given by the integration of the pressure and the shear stress, taking into account the fact that there is the fluid is viscous. So this brings generally in the models what we have is clear separation between different forces acting in different directions. So I do not know if you are familiar with this, but the drag is the aerodynamic force acting in the direction of the velocity. The lift is the aerodynamic force acting in the normal to the velocity. For longitudinal plane and taking into account also the attitude control, the pitching moment is should be also considered. This is just an example of 3 degree of freedom set of equations, dynamic equations considering the forces acting on the vehicle, and kinematic equations to take into account the position of the vehicle. Well, I keep talking about vehicles because for me it is for regarding spacecrafts, flying or re-entry vehicles, because most of the work up to now has been done in this area for ascent vehicles, so launch vehicles and re-entry vehicles. Okay. So, but these are the same equations that can be used for debris and could be used also for asteroids. This is a set of equations for the space, taking into account the fact that the Earth is spherical and rotating. Then there are simplifications that can be taken into account. Simplifications which basically take into account the fact that non-rotating, the Earth should be considered spherical, but could be, well, we could neglect the rotation. What are important for the trajectory computations are sometimes the ballistic factor and the lift factor, especially for non-lifting objects as the debris. The ballistic factor gives basically an idea of the trajectory that is followed in terms of zones or regions of the atmosphere which are passed through and when. So basically it is possible to have a rough estimation through the ballistic factor of the kind of trajectory and the kind of heating that is experienced by the non-lifting or the ballistic boat. Then we need to have models for the hydrothermal loads and the mechanical loads. Okay, this is probably the point where we can stop. Then we will have a more or less detailed review on all the tools that I mentioned before.
Okay, thank you. First part. Is there any question on this first part of the lecture for Edmondo? Yes, please.
Regarding the calculation of the casualty area, the casualty probability, I find it a little bit inconsistent with this 15 joule casualty energy. So the 15 joule is considered as the energy that can kill a person, or is that
Can
right?
injure a person.
An injure.
Injure, not kill.
Okay. So
That
when you
much.
calculate according to the formula of the area that reaches the ground,
Yes.
that formula encourages you to have the debris not breaking, because everything is concentrated and the area is minimized. But if you had the debris breaking, then probably many pieces would not reach the 15 joule threshold.
That is why you need to use the tools to see what happens.
Yeah, but I'm talking about international regulation and proposal for finding a metric that quantifies the actual risk for apparently it doesn't take into account this 15 joule.
No, the 15 joule is taken into account.
So the area that you are considering takes
There is-
away all the parts that don't reach this.
No, in order to have that amount of risk, based on the density of the population, based on the orbit of the debris, what can be computed is the amount of total casualty area, which gives which is a limit that takes into account those 15 joules.
So if there is a fragment that doesn't reach the 15 joule,
It's not
taken
considered.
away.
Yes, it's not considered. Yeah.
Yes.
Just one question about one of the things that you commented on, that most of the work has been done on ascent vehicles and re-entry vehicles. In transitioning to debris, one of the main differences, of course, is you're going from a controlled object to an uncontrolled one.
Yeah.
I was wondering, in that transition, if you can comment on what the biggest differences are that you have to do in the tooling or in the approach to dealing with.
Well, all the tools have simplifications on that, in the sense that, for example, not controlled object like a debris can tumble randomly, and this sometimes is taken into account in a simplified manner or is not taken into account at all. So these are simplified approaches, but basically every time that you, not all the times, but every time that you consider a simplification, you have a conservative evaluation of the risk, so higher risk. And that means, as I will explain, if that is the case, what you have to do is basically to enhance your models and go for better modeling of the tumbling and the aerothermodynamic characteristic, basically, because that is the major problem.
How do you validate these models? Because they are very completely different, and it is quite impossible at the end to compare them. So
Well, they try to compare the models. Basically, what they do is try to fit the data from some debris entry. Okay, and basically everyone says that the method is doing what should do. When they compare for the same case different approaches, what you have, for example, I will show tomorrow, it's a short comparison between ORSAT and SCARAP. And basically they have quite different results in terms of pieces that survive, dimensions of the pieces, and these kind of things. And basically the answer is at the end that both do what they have to do.
Okay, let's have a few minutes break and then we resume.